All right, welcome back, everybody. We're now going to go on to chapter 7, bones and bone tissue. All right, so starting off with our bone functions, I think shape is a pretty self-explanatory one. Obviously, our skeleton gives us our shape. It also gives us a lot of support. Um, Notably, the bones of the legs, pelvis, and the vertebral column really give us our support and structure. They're there for protection of delicate internal organs. That's part of the reason why we have a rib cage. That's a big protector of all that stuff. Movement itself, of course, our muscles actually are what contract to move, but they attach to our bones, and our bones give us that movement. And then the rib cage, besides the protective aspect, it also expands and contracts while we breathe and helps us to breathe. So more on a physiological side of things, you have bones role in electrolyte balance. So they release stuff like calcium and phosphorus, and that's needed for chemical reactions within the body. So when we're running low on those materials, our bones can release that into our bloodstream so that they can be utilized throughout the body. We'll talk about bone marrow a little bit more farther into the presentation, but this is a big site for red blood cell production. And then acid-base balance as well. So we talked about acid-base balance back when we were discussing homeostasis a few chapters ago. But bone plays a role in this as well. It can release alkaline salts to help maintain a stable pH. So if you remember, since they are alkaline, then they're going to try to help make it more basic. So if things are becoming too acidic, then alkaline salts can be released by bones to help bring that pH back to the 7.35 to 7.45 that our body likes to live at. Okay, so one of the ways that we classify bones is by their shape. So there's 4 different categories. We'll go into those each. So flat bones, like your skull or occiput, they tend to protect organs. They also can provide a large surface area for muscle attachments. Some examples of this is your skull. You have your scapula, your shoulder blades. They have a lot of muscle attachments. Your ribs have a lot of muscle attachments, and your sternum as well. All those would be considered flat bones. Long bones are what they sound like. They're nice and long. So they're longer than they are wide. You have your humerus as an example of that. Your femur is an example of that. And we'll talk about long bones a little bit more when we actually get into bone development and growth. Then we have short bones. Same thing. They're broader than they are long, so they tend to be a cube shape in general. Your carpal bones and your tarsal bones, your wrist and your ankle bones, that's examples of your short bones. And then you have irregular bones, which don't really fit into one of these other categories. So something like your vertebrae don't quite fit into a category, and they just have kind of various shapes and sizes. So there's no real defining characteristic other than the fact that they don't fit into our first 3 categories. Kind of a subclassification of irregular bones are sesamoid bones. And so these are small bones that are embedded in tendons. Your kneecap is an example of this. It's embedded in between your quadriceps tendon and your patellar tendon. You also have sesamoid bones on the bottom of your foot that run kind of just proximal to your big toe. All right, getting into the actual parts of the long bone, this is just kind of an overview here. And to zoom in, we'll go into this a little bit more in depth. Okay, so this stuff you definitely do need to know. I know it's a little bit definition heavy, but this is all important information on here. So we'll go from the top down. So your epiphysis is the head of each end of the long bone. It helps to strengthen the joint, and it provides a broad area of attachment for tendons and ligaments. So it has some, see kind of like the porous look to it, all the little holes. That's considered spongy bone, and so that's found in the epiphysis. You'll also see, I'm going to jump down here, guys. is the articular cartilage covering the top of the bone where the joint surface is. And so another word for articular cartilage is hyaline cartilage. You then have your central portion of the bone, and that is the diaphysis. It's thick, compact bone. We'll talk a little bit about the difference between spongy and compact bone a little further along, but just know compact bone is super strong. And one part of the epiphysis that I skipped past on accident is this little kind of line right here. That is your epiphyseal plate, which is your growth plate. And we'll go into that more when we talk about bone growth and development. Excuse me. All right, in the middle here is your medullary cavity. And so that's a central hollow portion of the bone that contains your bone marrow. You then have your endosteum, which is the inner membrane. This lines the medullary cavity. Then you have your periosteum, which is a dense membrane that covers the diaphysis. So the periosteum kind of helps keep everything held tight together, but it also will integrate into your tendons so that when the muscle attaches to the bone, that everything holds strong. All right, some properties of bone. Bones are really, really strong when it comes to tension and when it comes to compression. So both tensile strength and compressional strength in bones is very high. Collagen makes a big contribution to this tensile strength, so it can resist that stretch. And then in terms of the compression side of things, it's the calcium salts in bone that help it resist that strong squeezing force. So vertically, whether it's being stretched or compressed, very, very strong. What it does not do a good job of is its torsional strength. Bones do not like to be twisted. So typically, if you're going to have a fracture, it's the result of a torsional force. All right, actual bone cells, your osteoblasts help you to form bone, and your osteoclasts help you to dissolve your unwanted bone. So osteoblasts, you can remember that B and B, blasts build. And so they're responsible for osteoid synthesis. So that is made up of collagen and proteoglycans. That's what gives bone structure. And then clasts, C and C, clasts crush. So they get rid of the bone that we don't need or want anymore. And then you have osteocytes, which are mature osteoblasts, and they're actually embedded within the hardened bone. So they can do both jobs. They can do depositing of bone or building of bone and dissolving of bone, which is known as remodeling. And then, like we talked about earlier in bone functions, bone can put other materials into the bloodstream. So calcium and phosphate concentration within the blood is partly controlled by osteocytes. All right, bone marrow we talked about. Remember, that lies within your medullary cavity. There's two different types. Red marrow produces red blood cells. And so we start to lose this as we age. So when we're young and we need to develop a lot of red blood cells as our body is still growing, we have a lot of red marrow. And then as we get older, it changes to yellow marrow. And the reason it's yellow is because it's saturated with fat. And this is not a one-way street. So when red turns to yellow, that's kind of the norm. But if we needed more red blood cells, this yellow marrow can convert back into red marrow to begin producing new red blood cells again. All right, that brings us to our first review question. So which of the following is not a function of bone? A, electrolyte balance, B, blood production, C, acid-base balance, or D, regulation of blood glucose. So take a second and think about that one. So D, regulation of blood glucose is not done by the bones at all. So bone does help with electrolyte balance. It does help with our acid-base balance, and it does have a role in blood production. So if you need a reminder about those, pop up to the first couple slides. All right, types of bone tissue. This is where I was saying we'll get into the differences between compact bone and spongy bone. So compact bone, remember that's that diaphysis, the shaft of the long bone, and surfaces of other bones. So this is super strong and dense. You then have spongy bone, which you may also see called cancellous bone. And this is found in the ends of the long bones, that epiphysis. It can also be found in the middle of other bones. Okay, so this is an example or zoomed in version of the spongy bone. So you see there's compact bone here on the outside, and then these trabeculae is the name for this kind of lattice-like structure here, are filled with bone marrow. And so this structure here, even though it looks kind of funky, it's a way for the bone to stay really strong, but it also is very light because there's more space. It's not as densely packed as this compact bone. Compact bone, on the other hand, is very organized and compact. So we're going to go through a few more definitions here, and we're going to kind of walk through this diagram step by step. So the first thing that I want to point out is these circles here. See these circles? Those are called your lamella or lamellae. So that's the circles. And then you have a central canal within those lamellae. That's your Haversian canal, and that's where the blood vessels can run. And then you also have horizontal canals that connect these. That's your Volkmann's canal. So this is how we can transport blood throughout the bone, is these canals. So kind of this group or lamellae and the Haversian canal, those two combined, this little circle is considered an osteon. So that's the basic structural unit of bone. So osteoblasts and osteoclasts are the two types of cells that build and destroy bone. And then your osteocytes are your mature bone cells. So your osteocyte is your bone cell, but the osteon is the structural unit. I know they sound similar, but make sure you don't get those two things confused. So remember, cyte means cell. So osteocyte is a bone cell, and osteon is this structural unit. A couple other things to point out here. You'll see these little black dots scattered throughout. That's your lacunae, and that's where the osteocytes actually sit. And then you also have these little tiny passageways in here that connect the lamellae to each other. Those are called the canaliculi. So let's just go through it quickly again. You have your lamellae, or your circles, with the central canal. That's your Haversian canal. Those two things combined create your structural unit of an osteon. These lacunae are little gaps where the osteocytes are contained. The little passageways that connect your lamellae are your canaliculi. And then your horizontal canals are your Volkmann's canal, and that helps to transport blood and nutrients between the bones. Okay, so we just went over it twice, but I have another question for you. What is the basic structural unit of the bone? So think about that one. And I hope you all got that. That would be A, osteon. So remember, the lamellae and our Haversian canal create a structural unit called the osteon. The lacuna are the gaps between our rings of lamellae. The canaliculi are those microscopic passageways that connect our lamellae. And then, as we said, osteocyte is the bone cell itself. So that's our basic cell, but the osteon is our functional unit. Okay, we're going to talk a little bit more now about bone development and growth. This is done two different ways. So you have what's known as intramembranous ossification, and that's the ossification of fibrous connective tissue. So this doesn't happen super often in the body or at a lot of spaces. Your skull and your face. This is the best example of it, and this is the reason why we have soft spots on young babies' heads, is because it's going through this intramembranous ossification. And those soft spots are known as fontanelles. You'll see that in your textbook as one of our real life examples. What we're going to talk more about is endochondral ossification. And so that means the ossification of cartilage. And this primarily occurs in our long bones. It starts around 3 months of gestation. And this is a majority of bones. And so basically, the bones kind of evolve from cartilage. Okay, so you may want to follow along in your book. This diagram is right out of the book, but I think it does a good job of summarizing it. So as we said, about 3 months in, this endochondral ossification will start. And so initially, it's kind of these cartilaginous bones, and they almost, you can think of it as a model or a framework that the actual bone is going to follow. So chondrocytes are cartilage cells, and that makes up the majority of the bone initially. Slowly, osteoblasts are going to replace the chondrocytes. And so they begin to coat the diaphysis in a thin layer, and then they'll start to produce rings of bones that'll begin to encircle the diaphysis. And these blasts start to lay down bone, which causes the cartilage to start to calcify. So you then get some blood vessel penetration through the cartilage. And then that is how the primary ossification center develops. So the blood vessel will penetrate, it'll go in the middle. You already have some of the bone cells or osteoblasts kind of around the outside, but then they'll all start to gather around this blood vessel, because that's where all the nutrients are coming for those blasts to be able to lay down more bone. So that's your primary ossification center, is that central part. So that medullary cavity or your marrow cavity begins to fill with blood and stem cells. Remember, stem cells are unspecialized cells, and the ossification continues. So it'll move from the center here in the primary site in the diaphysis, and it'll expand outwards and upwards. And so that's why the bone starts to grow in length. And then eventually in your epiphysis or your ends, you will start to get secondary ossification centers, and we'll talk about that too. So quick summary, we have kind of a cartilage model or framework. The osteoblasts start to replace our chondrocytes and start laying down bone in the diaphysis. The blood vessel penetrates. We start to concentrate our osteoblasts and bone formation around those blood vessels. That's our primary ossification center. It starts to spread out through the diaphysis. It gets longer, and eventually it reaches the epiphysis, which is our secondary ossification center. All right, so bone growth itself. So lengthening occurs at the plate once we have more of a formed long bone. And so, like we said, at the top of our long bones, we have our articular cartilage or hyaline cartilage. And then you have your epiphyseal plate itself, our growth plate. So these cells start to kind of move towards the diaphysis, and minerals are deposited. And then just like our endochondral ossification that we just talked about, the osteoblasts start to replace chondrocytes, and the cartilage becomes calcified. And so basically, as long as chondrocytes are reproducing in here in the plate, the bone will continue to elongate. So that's what, if you've heard that someone's growth plate is still open, that means that there's still chondrocytes present in the epiphyseal plate. And then as we get older and more of that cartilage begins to calcify, our plate gets much thinner. So typically the window for a growth plate closing is 16 to 25. And you can see it really easily on an x-ray, actually, if you take an x-ray of a super young kid versus someone that's say 18 years old. You can find that on Google super easily too. You'll see a big difference on how it appears on an X-ray. So when we run out of chondrocytes and cartilage to replace and ossify, that's when we say our growth plate is closed. And so all you have left is this little thin line of spongy bone. That's called your epiphyseal line. And so, as we said, the growth plate or epiphyseal plate is really to deal with bone lengthening, while bone widening actually continues to take place throughout the lifespan. And what you'll see with bone widening is that they continue to make this cavity or medullary canal wider and wider. And then the compact bone continues to fill in on the outsides. All right, bone remodeling. This is the term we use for the process that continues with destroying old bone, known as resorption, and laying down new bone, known as ossification. So osteocytes are the primary ones that are doing that. That's that mature bone cell. So this is kind of influenced by age and how often a bone is actually used. And so basically it's a balance of osteoblast and osteoclast activity. So remember, blasts build, clasts crush. And so when we're young, our blasts much outwork our clasts. So we're building a lot more bone because we're growing. When we get into kind of our 20s, the balance starts to even out. We don't necessarily grow, but we don't lose either. And then once we get usually around age 40 and up, we actually start losing a little bit more bone than we are gaining. But it also is very much determined by activity. It's not just an age thing. So the more we use our bone, the more our body gets the stimulus that we need them to be strong. So basically, the more you're up, moving, exercising, all that stuff, the stronger your bones will be because your body knows that we need to use them. If we're just laying around and we're not using our bones, then the body kind of assumes, hey, I guess we don't need that as much, and they start to break them down. Okay, you'll see in your book that it goes over a few different types of fractures in terms of like the simple, compound, green stick, all that stuff. I think that's great to take a look at and get an idea of the different types of fractures. But I won't necessarily test you on the different types of fractures or show you a picture of a fracture and ask you to tell me what kind it is. So don't feel like you have to memorize those word for word, but I would like you to take a look at them and understand that fractures are classified by the kind of the type of break. The only other thing I want to touch on fracture-wise that's not in the slideshow here is just the difference between a closed reduction and an open reduction, because those of you going into the healthcare field will certainly hear those terms. So a closed reduction basically just means that they didn't need to do a surgery or open up to get to the bone to reset it. So someone breaks their arm, they put a hard cast on it, that's a closed reduction. Someone really breaks their arm and they have to go in and put pins and screws and plates to make sure that it sets and is held well. Now that would be considered an open reduction. So a term that you may see is open reduction internal fixation, ORIF or ORIF. And that is when they have to go in and put in hardware to actually reset the bone. All right, so what you do really need to know is how a fracture is repaired. So we're going to go kind of step by step here. So when you first get that break, you get bleeding. So there's blood vessels and bone in the periosteum. They're all torn. It starts bleeding. You start forming a clot or a hematoma, and that starts our healing process. That has all the inflammatory and other cells to start our healing process. That hematoma and clot end up turning into what is known as granulation tissue, which is kind of our very immature tissue. But that granulation tissue has inflammatory cells, bone forming cells, all the materials we need to start repairing that bone. So the granulation tissue has a lot of collagen and fiber cartilage, and so it's what's considered a soft callus. As bone starts forming, it becomes a hard callus and it kind of splints the two ends of the bone together. So it repairs it, and it almost is got too much material right now. So you can kind of see it bump out there. That's your hard callus. And then eventually your body starts to realize, okay, we don't need quite this much. And they can do that remodeling and build what they need to and take away what they don't. And we get our bone all the way healed. So I always tell patients that end up breaking a bone, not that it's enjoyable at all, but you're much better off breaking a bone than you are tearing a tendon or a ligament or something along those lines, because bones are really, really good at repairing themselves and remodeling, and they're going to be 100% as strong as they were before the fracture, if not even stronger. And that's not always the case with other structures. So kind of quick summary, we'll go back through this again. When the fracture happens, blood vessels break. That forms your clot and hematoma. And that kind of starts our inflammatory response, brings everything we need to start healing there. That hematoma transitions into granulation tissue that has collagen and fibrocartilage that becomes a soft callus here. The bone cells start producing a bony callus or a hard callus around it. The kind of heals the two ends of the bone together. And then over time, we remodel to build up what we need to, take away what we don't need, and we have our bone again. All right, last review question for this lecture. So which portion of the bone does the primary ossification center begin? A, epiphysis, B, diaphysis, C, the epiphyseal plate, or D, the periosteum. So think back to when we were discussing our bone growth, our endochondral ossification. And your answer is B, the diaphysis. So the epiphysis is an ossification center, but it's a secondary ossification center. So our bone starts in the middle and works its way out. The epiphyseal plate contains chondrocytes, and it's one of the last areas to ossify. And then the periosteum is the outer covering of the bone. Even though it has blood vessels and helps get the nutrients to the bone, it doesn't actually really play a role in ossification itself. And that is everything for chapter 7.